Hello, I am the Korean PLC expert. Today I will explain part 3 of the sequence and the DECO commands, specifically the DECO command. DECO command is a decode command that turns only bit and a position corresponding to a binary value in a specific word device. It may seem complicated at first, but simply put, it works as follows. For example, if you write the decoded result of D0, S is D0, and D is M0, D0 to, okay, I write S is D0, D is M0. Then when D0's value is 5 bits and 5 is turned on. Or when D0's value is 10 bits and 10 is turned on. This command is mainly used for step control. The Merced Q series supports as a 256 6-bit decoder. 2 to the d power of 8. 2 to the d power of 8. Okay, 2 to the d power of 8. 256. Now let me explain the principle behind the decode. This is the logic circuit diagram of a 2 to the power of 2 or 2 by 4 decoder. I will explain this logic circuit diagram step by step. There are two inputs, in I0 and I1, and four outputs, O0, O1, O2, and O3. First, let's look at the possible input combinations. I0, I1, 0, 0, 1, 0, 0, 1, 1, 1. There are four cases, 0, 0, 0, 1, 1, 0, and 1, 1. And we will see how the outputs change according to these cases. As you can see, the logic gate function as follows. First, the NOT gates. NOT gates outputs the inverse of its input. For example, 0 is output 1, 1 input output 0. Next, the AND gates. AND gates outputs true only when both of its inputs are true. True is a true. Now, let's assign value to I0 and I1 and observe the results. I will represent I0, and in red, I1 in blue. First consider I0, 0 equals 0 and I1 equals 0. I0. The 0 from I0 travels along the line and at the first branch. Split into a downward signal and one that goes straight. The downward going signal further split, and the signals that do not pass through and NOT gate remain 0. First, the first input of O1 and O3 receive pulse. Then, let's look at the signal passing through the NOT gates. After passing through the NOT gates, 0, becomes 1. So the first impulse of O0 and O2 receive true. Next, the I1. I1 is 0. I1, the 0 from I1 travel along these lines and at the first branch, spread into the downward signal and one that goes straight. The downward signal sends pulse to the second impulse of O2 and O3. The signal passing through the NOT gates become 1, so the second input of O0 and O1 receive true. So now let's look at the value of O0 through O. Okay, change color. Pink. I'll change color red. Okay, pop. O1, O0 through true. It's a true. O1 receive a pulse and true, so it offers pulse. O2 true and pulse output is 0. O3 first pulse output is pulse. In the case of 0, 0, is output is O0 is true and O1, O2, O3 is a pulse. Next, consider the case where I will erase the red change. Okay. Next, consider the case where is I0 equal 1, I1 equals 0. I0 equals 1, I1 equals 0. The 1 from I0 travels along the line and at the first branch split into a downward signal and one that goes straight to. The downward signal also splits, and the signals that do not pass through or NOT gates remain 1. 1, 1. True. First, the first input of O0 and O3 receive true. Then, let's look at the signal passing through the NOT gates. After passing NOT gates, 1 becomes 0. So the first input of O0 and O2 receives pulse. Next, I1. From the I1, the 0 from the I1 travels along its line and at the first branch, right? The downward signal sends pulse to the second input of O2 and O3. These signals passing through the NOT gates becomes 1, so the second input of 0 and 1, 0 and O1 receive true. Okay. Now let's look at value of O0 through O3. O1 pulse true equal pulse. O1 true is a true. O2 receive a pulse and pulse, so it outputs pulse. O3 receive true and pulse, so it outputs pulse. Okay. In the case of I1 equal 1, I0 equal 1, I1 equal 0, output O1 is true. What can we deduce from all of this? I0 and I1, the inputs I0 and I1 can be represented as decimal numbers in binary form. Zero zero is 0, 1 0 is equal to 1, 1 0 1 equal to 2, 1 1 equals 3, 0 0 equals 0. And the decoder turns on the corresponding bit among the outputs O1 through O3 based on the decoded result. And should we check how it was created using a PS program? First, I created a ladder that uses the DECO command, DECO, D10, M10, K2. Then I will create a ladder that mimics the DECO logic gate. We need to create a ladder program that accommodates the four cases explained earlier, right? Okay, the 0.1 is I1, case 1, case 2, case 3, case 4, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1. And the output is M0, M1, M2, M3. Is completed. Let's first take a look at the ladder program that functions like a logic gate. Okay, start to simulate this. There are I0 and I1. You can see that when both I1 and I0 are 0, and M0 is turned on. And when I0 equal 0, I1 equal 1, and I1 equal 1, M2 turns on. Then, what about the DECO commands? Okay, M10 and monitoring of D10. When a 0 is input to D10, M10 is turned on, and when 2 is input, D10, M12 is turned on. Thus, we can confirm that DECO is a decode command that turns on the bit corresponding to a binary value in a specific word device. And the advantages of DECO command are as follows. Also, one drawback is that using M of V step numbers for step controller does not allow multi-condition searches like KN plus D0, making it difficult to trace the program when it becomes complex. With the DECO commands, step control yields a single output, which makes it easier to verify which part of the process the step is connected to. Okay, that's all for today. Thanks for your hard work.